Okay, welcome back. We're going to talk about redox reactions today. It's also called electron transfer reactions. If you took my chemistry course last year, or previously, this is a chapter that we didn't get to, unfortunately. So this is going to be kind of new. For redox reactions, one thing that I would like you to know, pardon the bad handwriting, is going to be this very simple expression, Leo goes grr. And I'm really slow at writing on the keypad, so I do apologize for that. But Leo goes grr. It's a very easy saying. Please write that down, and you can stop the video at any time to take notes. That'll help us understand what's oxidized and what's reduced, because what it stands for is lose electrons oxidized, gain electrons reduced. So that's Leo goes grr. What we have here is an image of magnesium ribbon that's burning. It's on fire here. So the way we could do that is to write a pretty easy balanced equation. Would be, magnesium plus O2 yields MgO, and then we'd balance it from there. With redox reactions, we actually start with the electrons, and we can work our way back as well, but we'll start with the electrons here. Magnesium wants to have a 2+ charge, and we'll talk more about that later. And so to get there, it needs to lose 4 electrons. Now, oxygen wants to have a 2- charge, and to get there, it needs to gain 4 electrons, because remember, electrons are negatively charged particles. So for magnesium to give up those 4 electrons, it's lost electrons. So magnesium is oxidized. That's oxidation. Now reduction is gaining electrons. Like I told you, Leo goes grr, and oxygen gains electrons. So that's the reduction. So what it looks like is something like 2 magnesium plus oxygen plus 4 electrons yields 2 magnesium plus oxygen plus 4 electrons. And so just like we've done before with spectator ions, we cancel out the stuff that's on both sides, which in this case is 4 electrons. So what we're left with is 2Mg plus O2 yields 2MgO. Now, for you guys, you could just as well look at this reaction, write this portion, and then work your way back to what's reduced, what's oxidized, what are our oxidation numbers. And that's really the way I prefer to do it. But that's probably because that's the only way I know how to do it, and that's not your guys' fault, that's mine. Here's a little image we got from your book. It talks about submerging a zinc bar in copper sulfate and emerging copper in silver nitrate solutions, and they're both just redox reactions. So let's look at them here in the molecular formula side of things. What we can see is zinc is coming and bonding with sulfate, and it's kind of kicking copper out on its own as a metal. If you memorize polyatomic ions and their charges in chapter 2, then this is going to be super easy. If not, it'll be kind of weird for a while, but we'll get through it. So zinc likes to have a 2+ charge, so it needs to give up 2 electrons. Copper is going to gain those 2 electrons to become just stable copper. So if zinc is giving up 2 electrons, it's oxidized. And so here's something that's confusing. If an atom is oxidized, then it's called the reducing agent. How confusing is that? Maybe it makes good sense to you. I hope it does. Copper is reduced. So if it reduced, it is the oxidizing agent. So it's reduced because it oxidizes zinc. So it's the oxidizing agent. Zinc is oxidized because it reduced copper, so it's a reducing agent. It kind of makes sense if you think about it, but it's weird to say unoxidized element's a reducing agent. Here's a problem that you could see, something like this, that we could solve. Copper wire, so just plain old copper, reacts with silver nitrate, so it's AgNO3, to form a silver metal. Charges would be helpful, but I think we could definitely do it. So the question is, what's the oxidizing agent? So what's losing electrons is our question. So you'd write out your chemical equation. Copper solid, AgNO3 goes to copper nitrate plus solid silver metal. And then you'd balance it, which if you know your charge is not too bad. And then you say, okay, well, what was oxidized? What lost electrons? And so you'd have to say, okay, copper had to give up 2 electrons to become copper 2 plus. And we know that because the nitrate has a -1 charge on the whole nitrate ion. And copper, to balance it, would have to be up here, a +2. And we'll look at that more. And my handwriting, I assure you, will probably just get worse. And then silver, plus 1 electron becomes just plain old silver. And we know that because here we've got our nitrate ion again as its -1. And so to be balanced, silver is going to have to be -3, +3. And so then we're going to gain an electron to get silver to its +2, which is pretty stable for silver. So silver is reduced. So if silver is reduced, then it is the oxidizing agent, and we've answered that question. So we will practice more of those. Oxidation number is the stuff that gets really helpful. The charge an atom would have in a molecule if electrons were completely transferred. And you're going to see it's kind of what I had already drawn for you a little bit. Free elements have an oxidation number of 0. So things like sodium and beryllium that can exist on their own, lead can exist on its own, hydrogen gas bonded to itself, oxygen bonded to itself, these all have an oxidation number of 0. They're not really going to want to share or give up electrons to anybody else. They're very stable as they are. In monoatomic ions, the oxidation number is equal to the charge of the ion. So here, Li plus would be a +1, Fe3 plus is a +3, O2 minus is a -2, and those are pretty easy to work with as well. The oxidation of oxygen is usually -2. Pretty much operate on that and you'll be in a safe place. There are some exceptions. Hydrogen peroxide, for example, hydrogen's a +1, oxygen's a -1, because hydrogen peroxide as a whole has to be balanced. And so to balance it, oxygen has to be a -1. So for hydrogen, it's normally going to be a +1. It's a pretty safe bet if you don't know to guess +1 for hydrogen, except if it's bonded to metals in binary compounds, then it can actually be a -1. Group 1A metals are all +1, and we'll see that on a chart here in just a second. Group 2A metals are +2, fluorine's always -1. And the sum of the oxidation numbers of all atoms in a molecular ion is equal to the charge on the molecular ion. A lot of our molecules aren't going to have a net charge, but if something we work with does have a charge, we want to make sure that all of our oxidation numbers sum to the charge of that ion. For molecules, we'll normally want them to sum to 0, and we'll try that in just a little bit. Here's a tricky one, kind of a pain. Oxidation numbers do not have to be integers. Bummer. They can be fractions. Yikes. So let's practice one. What are the oxidation numbers in all the elements of HCO3 minus? And so they kind of start us off with a little bit of a tricky one because we got to deal with this pesky minus. Not too bad. It's really not. But when we're all done and we add up all the atoms, they all need to add up to a -1. So let's start with what I told you before. Oxygen is normally a -2. So we'll start there, -2. Now since we have 3 of them, that makes all of our oxygens a -6. Very easy. Now we also said hydrogen is normally a +1. And so we have a +1 and a -6. So right now we're kind of at -5, and we want to be at -1. And so to get there, carbon must be a +4. And if you know carbon, it can make 4 bonds, 4 single bonds. So +4 is a viable option for an oxidation number for carbon. And so we've got +1, +4. That makes +5, -6, -1. And that's the charge on the whole ion. So we're pretty likely, we really only knew 1 to start with, and we figured out the rest just by pretty simple math. So oxygen's a -2, hydrogen's a +1. They set up this neat little algebra doodad, and carbon's 4. Great. So we were right. Okay, now here's a useful chart. If anybody finds this in their book, please let me know. Haven't seen it yet. I'm hoping it's in there somewhere. It's oxidation numbers. It's great. Here's hydrogen and all of our group 1, they're all plus 1s just like you'd think. Here group 2, they're all plus 2s just like you'd think. Because again, if you remember that octet rule, if they can just lose one, they've got that stable outermost shell. And then here we've got transition metals where business gets weird. You'll see +6, +5, +4, +3, +2. It's like, holy smokes, they're all over the place in here. Then we get to a little more logical place where fluorine, normally a -1. Chlorine, normally a -1. Bromine, normally a -1. But even here, there's a lot of variations. Oxygen, normally a -2, but there's a lot of variation. So I wish it were as simple and linear as -1, -2, -3. But it's not. So we will have to work with these, and the more we work with them, the more familiar we'll become with them. So why don't you take a second, please, pause the video, and see if you can solve oxidation numbers for all of the elements in each of these compounds. Okay, welcome back. Hopefully you did it. And hopefully what you find is close to what I find, assuming I'm doing them right. If it's not, then pause it after the first one and try again, because practice is a good thing. So if I were to solve this, which I'm going to try, I would say let's start with oxygen as a -2, because most of the time that's what it is. So that gives me a -6 in here. Now sodium's in that very first group, so I'm going to go ahead and say sodium is probably a +1. So if I've got -6 +1 and my whole charge on this compound is neutral, then I suppose I'd need +5 for iodine. So +1, +5, -6. Yep, that's neutral. Looks good to me. I hope that's right. Let's see. +1, -2. +5. Got it. Not too bad. Okay, let's look at IF7. This one's really not too bad because fluorine, we had that word always, which is great. So -1 gives me a -7. So iodine must be +7. Let's see how we did. Got it. Okay. Little trickier one now, but we can still do it. Oxygen, -2. Okay. Potassium is in that first group, +1. So now we've got a -14 and a +2 because there's 2 potassiums. So +2, -14. So to get to neutral, I suppose I'd need a +6 because there's 2 chromiums here. So we'll throw a +6 in here, and we should be pretty well neutral. Let's take a look at how we did. Oxygen's -2, potassium's +1, and +6. Got it. So hopefully that's not too terrible. Types of oxidation reduction reactions. These aren't too bad, but there are some things you need to know. Combination reaction, A plus B yields C. We're building something up. So here we have aluminum plus bromine gives 2 aluminum bromide. And you could find their oxidation numbers pretty easy because this will be 0, this will be 0, bromine will be -1, and if there's 3 of them, then you just balance it from there. So it's really not too bad. I mean, once you practice with them, just like anything, the more you practice, the better you'll get at them. So there's also decomposition. These probably sound familiar to you from Gen Chem, where something larger breaks down into its individual parts. Here's potassium chlorate probably. Yields potassium chloride and oxygen, and again you could balance this. This would be 0, chlorine's -1, potassium's a +1, on and on and on it goes. So potassium's a +1, oxygen's a -2, and you could find your chlorine having known those. So hopefully not too bad. Combustion is something plus oxygen yields B. Earlier we learned that in combustion it yields CO2 plus water. That's not always the case. It's normally, but here's one where it doesn't. Sulfur plus oxygen yields sulfur dioxide. And so again, 0 because sulfur's on its own. Oxygen bonded to itself would be 0. And then sulfur dioxide, oxygen would be a -2. And sulfur, you just have to balance it from there. So hopefully not too bad. Magnesium oxide, we don't have to dwell on too long because we just did it. At the very first slide we looked at was balancing this. So magnesium on its own is a 0. Oxygen on its own is a 0. And then you balance them from there. Oxygen is going to be a -2 because that's normally what it is. And magnesium, to balance it's a +2. So in my opinion, it's easier to start here and then work your way to those half reactions if it's necessary, because I think the half reactions are a little tricky. So a displacement reaction, to be displaced is to be kind of kicked out. So here A wants to bond with C, so B is kicked out on its own. That's displacement. And there's a few types of those that you'll need to know. Here we have strontium and water, and the strontium is strong enough to bond to that OH minus, and hydrogen is kicked out on its own. So we're going to call that hydrogen displacement. And again, you could find oxidation numbers for all these. Strontium would be 0. Here the OH minus ion is a -1. There's 2 of them, so this is very likely a +2. Things like that we've done before. They're really not too bad. Here's your oxidation numbers. What else we need? Titanium chloride plus magnesium gives us titanium on its own plus magnesium chloride. And so that is called a metal displacement because what's kicked out is a metal. Again, oxidation numbers, not too bad. Chlorine, like we've talked about before, is pretty much going to be a -1. Not always, but it's a pretty safe guess. So if this is a -1 and there's 4 of them, titanium's probably a +4. Magnesium's on its own, so it's 0. Titanium's on its own here, so it's probably a 0. And chlorine is probably a -1, and there's 2 of them, and magnesium is probably a +2 to balance it. Sorry about the sloppy 2. Okay, easy peasy. So here we've got chlorine bonding with potassium and kicking bromine out on its own. And so since bromine's been displaced, that's called halogen displacement. You'll remember, I hope, from Gen Chem that halogens are fluorine, chlorine, bromine, iodine, those guys, right before we get to noble gases. Again, you could solve for oxidation numbers without too much trouble, especially since it's -1s and +1s across the board. Should be pretty easy for you. Okay, so the activity series for metals is something that in the past we've really only talked about briefly, but basically it's how reactive metals are. We did it by making a hollow penny in chemistry where we were able to dissolve out the zinc, which was really rather reactive with our hydrochloric acid, in a newer penny and leave behind the copper, which would not react with the acid. It was a really easy demonstration to show this. It was kind of fun. Hydrogen displacement reactions would be where our metals will react to produce H2 gas. And so these that are most reactive, they'll react with cold water, like sodium. Just drop a little tiny piece of sodium in water, it reacts on its own. These further down need a little more energy to get that reaction started. So they don't need water, they need steam to produce that hydrogen gas. These down here need even more to get started, so they have to have an acid. And then these down here won't react with acids or produce or water to produce hydrogen. So that's hydrogen displacement. They give us kind of a convoluted formula for it with all these. M is a metal, BC is acid or water, okie dokies. B is hydrogen. Great. Looks great. So here's an example with calcium plus water gives us calcium hydroxide and hydrogen gas. It's balanced. The charges make sense. So we look up here at our chart and we say, is this realistic? Calcium, got it. Reacts with cold water. Okay, cool. Yeah, I can buy that. Then they show the same thing, where again, the charges are balanced, it looks realistic. You say lead reacting with cold water. And so you look at your chart, lead. Here it is. Lead will react with acids to produce hydrogen, but it won't react with water. So you say this, even though on paper it looks good, is not realistic. So if we're looking at just halogens, fluorine, chlorine, bromine, and iodine, they have an activity series of their own, and it's really rather simple if you remember electronegativity from Gen Chem. Fluorine is stronger than chlorine, chlorine is stronger than bromine, bromine is stronger than iodine, and by that I just mean how reactive they are. Fluorine's easy to remember because it's at the very top right of our periodic table, and it is the most electronegative element. It's the most greedy for electrons. And so if we look at reactions where we try to displace these things, we see that chlorine wants to bond to potassium because chlorine is negatively charged, potassium is positively charged, and it kicks bromine out. So we look at this and we say, is this realistic? Is chlorine more reactive than bromine to kick it out? And we say, yes it is. This makes sense. And here it is, occurring on a rather large scale. And oxidation numbers would be pretty easy. Negative ones and positive ones across the board, no problem. And here we look at another reaction where we say we've got iodine plus potassium bromide gives us potassium iodide. So you say, okay, is iodine reactive enough to kick bromine out on its own? You look up here and you say, no it's not. Iodine's the weakest. It's not going to be able to kick bromine out. So even though the charges are balanced and it looks good on paper, it's not realistic. So, other types of redox reactions that you should know. It's a disproportionation reaction. This is going to be a little weird. The same element is simultaneously oxidized and reduced. Oh boy. So, here's an example. Great. Chlorine gas plus hydroxide ions gives us ClO minus, Cl minus, and water. And so how can something be oxidized and reduced at the same time? Well, this diatomic chlorine that starts as 0 is going to become two different parts of our product. And so that's where we get just kind of weird numbers, because here oxygen is probably going to be a -2. And the whole thing has a -1 charge on it. And so this must be a +1. And this chlorine tells us that it's a -1. So we go, oh boy, we have two different. Well, let's look at it. So +1 and the -1, I just showed you why. And so here, chlorine has become a +1, so it lost electrons to become positive. That's oxidized. Leo, lose electrons, oxidized. The other chlorine gained an electron, so it's reduced. That's the GR part, gain electrons, reduction. So a little tricky. This asks us to classify each of the following reactions, and this isn't for a lot of what we just did. This is a little broader classification. So here we have calcium plus a carbonate gives us calcium carbonate, and that's precipitation, where we have solids settle out. Here we have NH3 plus hydrogen, so hydrogen's being donated and accepted. That's acid-base reactions. Here we have zinc and HCl gives us zinc chloride and hydrogen. That's going to be a redox, and you could say an H2 displacement because it is displacing hydrogen. And here's calcium and fluorine forming their compound, calcium fluoride. That would be another redox, a combination redox. So there's some examples of how we could do those relatively easily. And this is where we're going to end. What's commonly called the breathalyzer test works off of a redox example. So here you've got chromium as a +6. Here you've got chromium as a +3. And basically the way it works is this on the reactant side is ethanol, an ethyl alcohol. This is the alcohol that's consumable, at least without really terrible effects, some terrible effects, by humans. And if there's more alcohol in the person's breath, what it's going to do is cause this redox reaction to shift from the potassium chromate to the chromium sulfate. And when it does that, it works kind of like an indicator, like our acid-base indicators, where when you add something, it changes colors. It works a lot like that. Here, this is an orange compound, and this compound is more green. And so basically, as this person is breathing in, if there's alcohol in the breath travels in, the ethanol is dissolved in as bubbles, and it will push this reaction to the right. And then it will become more green in here. And it's all in this nice little handheld deal. The light shines through. Depending on how orange or green it is, this is going to detect that color, and then it will show up on the meter as a number, and that's your 0.02 0.04, blood alcohol content kind of numbers. And so it's a decent example of applied redox reactions, and that is where we will stop today.